Hello everyone. My name is Juno Park from Maju University, and today I'm gonna talk about my research titled Optimizing Routes for Integrated Automated Vehicle Testing Scenarios. And this is content, the introduction, methodology, and research. And specific things I'm gonna explain it about in each slice. And first one, research background. I'm not sure about you guys know these things, but in Hwasong, there's a automated vehicles test bed named KAIST. It's ready for testing automated vehicles. So we basically provide the basic scenario to test the vehicles. And when the users want to test their vehicles, they can select the scenarios from the basic scenarios, and we validate the vehicle's performance. But there's a lot of scenarios and the space and the time limit, so we have to make a test more efficient. So we need to make some route, the optimization route to testing automated vehicles. So we just want to optimal zone combination for full scenarios coverage and generating optimal routes based on the drive combinations. And I review the literature review, and recent studies about optimal routes is under complex constraints like traffic congestions or road congestions, or considering the stop location or waiting time. And also a review about the genetic algorithms. And the genetic algorithm is about find near optimal solutions, not the best solution. So it is used in the large, something have large search space and multiple constraints. And also in case of integer programming, programming was used to guarantee the optimal solution for find something. So we can make sure that generic algorithm is find the near optimal solutions, but integer programming can find the optimal solutions. This is the difference. And more specific about generic algorithm is based on the principle that the fitter individuals will survive. So there's a lot of the concepts like initialization, fitness evaluation, the selection, crossover, mutation, and iteration. It's like a nature genetic. There's the first generation, and we can say it's like parent generation, and each individuals have some features from fathers and mother, and then they go to the child generation. And there's a crossover, and sometimes the mutations happen, so we can maintain the diversity. And so it is repeated and repeat, so we can find the optimal solution at the end. And next one is integer programming. As I said before, it is to guarantee the optimal solutions. So optimizing an object function with all variables restrict to integer value. It's kind of linear programming, but all the variables are only for the integers. So it is there is an object function, constraints, and decision variables. The object function is something to minimize or maximize in this case, and the constraints can be like the expressions defining relationships or limits, and the variables can be like a distance, number of vehicles, or number of peoples. And this one is the basic about the KAIST. As I said before, it's the automated vehicles, the test bed. In this KAIST, we are gonna testing the automated vehicles across the 5 main zones. There's the highway section, urban road, community road, roundabout, and suburban road. And there's have some characteristics of each zone, like highway speed limit is 120 km/h, And like urban road and community road is have a like, signal intersection, like these kind of things. So each zone has their features, so we have to choose the zone to testing the scenarios. And next one is about test scenarios. KCD basically provides 27 test scenarios, and it has 47 test case. Test case is in the test scenarios. So test scenarios can be divided into multiple test cases. So we can see in the table, the one scenario could have 2 test cases. And the KCD, all 47 test cases must be performed to validate the automated vehicles. So we have to choose which zone have to select it as to testing the test cases. And next one is methodology about my research. The first one is, in the whole methodology, I divide the methodology into 2 main steps. The number 1 step is assign the testable zone to each scenarios. Like in scenario 1 is gonna conduct it in highway. Number 2, scenario 2 is urban road, like these kind of things. And step 2 is generate the shortest route that satisfies the constraints, like which scenario is conducted in which zone. So in the table, you can see the step 1 and step 2. In the first one, there's the 5 zones, so highway, urban, community, suburban, and roundabout. And the number means the visit count. So it means in the 47 scenarios, how many scenarios visit the highway, how many scenarios visit the urban road. And after we assign the testable zone of each scenario, we're gonna move to step 2. It is route optimization. So we generate the shortest route of each combination, and we compare of the combination. So after all, we can find the best route of the test cases. So I propose a hybrid approach combining genetic algorithm and integer programming. In the step 1, in the more bigger one, is use the generic algorithm, and step 2, a more specific one, can be used as the integer programming. So we can see in the picture below, we use the generic algorithm to efficiently search through the large solution space. As I told you before, there's 47 test cases, and there's 5 zone can be chosen. So more than 30 billion cases can be possible. We think about when the combination of all the scenarios. So there's so huge space. So to efficiently find the near optimal solution, we use the generic algorithm at the step 1. And step 2, we are gonna find the shortest route using the integer programming, because we have to find the best solution of the combinations. So we use the integer programming to guarantee the best solutions. So combining GA to generate visit combinations and use integer programming to generate the shortest route for each combination. And after all, we can find the best one, and that is the shortest route of the testing all the test scenarios. And to initialize the generic algorithm, at the first, we have to randomly assign the one testable zone to each test case. It means like there's 47 test cases, and they have like multiple zones that can be tested. So we have to choose just one zone per one test case. So in the table at the below, like number 1 scenario, there's a test case 1 and 2. The red one is the selected zone. Like in test case 1, we have to choose the urban road, and test case 2 means the test we're gonna conduct it in suburban road. And after that, we have the zone combination. Like we have to visit 10 times per highway, 7 times per urban load, like this. So after find the zone combination, we conduct integer programming. So we can generate the shortest route using integer programming. And we comparison all the combination, and we compare the route lengths. We find the best one. So it's the more explain about the generic algorithm. There's a parent generation and child generation, and there's a crossover over the generation. So we get like mother's one, father's one, and they go to the child's one. And sometimes there's a mutation, like in the parent generation, the scenario like 7 choose the urban road, but at the child's generation, the scenario 7 choose the highway to test the automated vehicles. This is the mutation, and they repeat and repeat. The final one is we can say is the best route for testing automated vehicles. So this is the result of my research. In the table, there's a test case, the whole 47 test case, and there's a assigned zone at the right. So we can see a lot of the zones in there, and we find the optimal routes for the visit highway 9 times, urban road 16 times, community road 16 times, suburban road 2 times, and roundabout 4 times. And after that, we generate the route for using like integer programming. So we got the route, but there's the whole route is so long, and we have the time limit and the space limit. We cannot conduct 47 scenarios in a row, so we have to divide this route. And the generated routes are divided into 5 separate routes, and it is all starting from the highway zone. So there's a 5 routes in the middle of the slide, and the route 1 repeated twice. Route 2 are gonna repeat 4 times, and 3, 4, 5s are repeated just once. So total of 9 test cycles across the K-City will be conducted for testing the automated vehicle for 47 test cases. And the number 2 route is in the bottom. And next slide, you can see the route 3, 4, and 5. And the conclusion, I found the optimal route for the testing automated vehicle at the K-City. There's a 47 test case, and 5 zone are in K-City. So we find the shortest route to conduct the testing. And we can recommend when the test user come to K-City, and they have no idea about how to testing the automated vehicles, we can suggest this route for the optimal route, and they can choose which scenario will be conducted. So in the case, by combining the selected scenarios with the 5 generated routes, we can customize the test route, and it can be provided to the test users. And one of the research contribution is we considering both test-based zone and scenario-specific characteristics. There's a 5 zone on the K-City, and each scenario have a specific available zone. And we considering both, and we provide the optimal routes for the testings. But we still have some limitation, and we have to do further research. One of the limitation is we cannot consider about the behavioral characteristics of automated vehicle testings. So we can say that some scenario have a straight driving, but some scenario have a right turn or left turn or U-turn. but we did not consider about the behavioral characteristics of each scenario. And the second one is, it does not assume the multiple automated vehicles operating at the K-City. We assume that there's only one driving in the K-City, but at the future, when the K-City really testing the automated vehicles, they can be multiple automated vehicle in the K-City. So in the future, we have to do more research about considering behavioral characteristics of automated vehicle and thinking about multiple automated vehicles or testing their vehicles in the K-City. Thank you for listening, and feel free to ask any question you have. Thank you.
All right, I think the floor is now open for questions from the crowd. I know there's no more lunch, but you should ask questions. Okay. You have one?
Hi, thank you for the presentation.
Thank you.
So, is it part of the R&D project that you're involved, or?
Sorry, I can hear you.
Part of your R&D project?
Oh,
this
yes.
research part of the R&D project?
Yes, right.
So, you picked the KC because of your R&D project, right?
Yes, right.
So, I wanted to ask you the reason why you choose the zone level. So, it's an optimization process of choosing the optimal sequential zones, right?
Optimal sequence for what?
For the optimal route planning.
Yes. I just explained it.
Yeah. So is there any reason why you choose the zone level instead of like just doing the optimization? You choose the zone level optimization, right?
You mean the zone?
Yeah. So
Each scenario has an available zone, and you ask about why I choose the zone.
The size is the zone size. It's not larger, it's not smaller.
okay. I'll talk in Korean.
Okay.
그 돈 단위로 이걸 옵티마이즈하는 특별한 이유가 있는지, 그리고 여기는 그 작은 사이즈니까 조금 다양한 그 링크 노드가 없을 것 같은데, 지금 이게 좀 큰 사이즈의 종으로 가면 그거에 대해서는 어떻게 해결이 될지에 대해 생각도 있는지.
Okay, I'll also explain in Korean. Sorry for foreign students. 일단 이 존이 잠시만요. 이 존을 구분한 이유는 실제로 KCT에서도 이렇게 존을 구분해서 테스트하는 거를 그렇게 설정을 하고 있고, 이게 조금 더 큰 곳으로 확장했을 때를 생각을 하고 있습니다. 지금 실제로 이거를 가지고 저 화성시에 있는 리빙랩에다가 입혀가지고 이걸 어떻게 효율적으로 할지에 대해서도 연구를 진행하고 있는데, 그 부분은 아직 조금 더 구체화된 게 없어서 설명드리긴 좀 어려울 것 같고, 일단 이 존을 구분한 이유는 실제로 이거 저희는 KCT를 운영하는 입장에서 실제로 이 원리를 따라야 하기 때문에 존을 이렇게 설정했다라고 보시면 될 것 같습니다. 네, 감사합니다.
Thank you. Actually, just to I'm also a bit curious about that answer. If I understand it correctly, aside from the optimal route, like having the shortest path, is one of the objectives like for the route to visit each zone? Is that required for the objective of the function? Like, do you have to visit all zones? Is that part of the algorithm?
It is not necessary to visit every zone.
I see.
Yes.
Okay. Anyway, I think we have one more question here.
First, thank you for your interesting topics for presenting for us. I'm Jun, supervisor 2018 at KAIST. Could you move to two slide next probably, the combination table? Yeah.
Combination, okay.
Yeah. I was wondering that you put all 47 scenarios for the 5 zones, right?
Yes, right.
So you put the numbers and information of the whole numbers in one row should be 47, but I'm just wondering how you distribute the numbers. Yeah. Is there any rule or law you follow? Or you just put the numbers randomly? Or you set the minimum visit counts or maximum visit counts per the zones?
I did not setting some rules to visit like minimum or maximum thing. But there's some scenarios like roundabout scenario can be conducted in only roundabout zone. It can be like affect the visit counts in the combination, but there's some other things to like restrict the visit counts for each zones. I did not do anything for them.
Thank you for answering.
Yeah, thank you.
Do we have other questions from the crowd? Going once? Twice? I just want to add up on what my previous question. I think it's also interesting to somehow, I don't know if you can add it, but since you have different zones and it is a test for automated vehicles, maybe in the future, maybe the optimized route can consider like, I don't know, visiting each zone so that maybe you can focus on how the automated vehicle behaves as it changes to another zone.
Yes.
So I don't know if that would help in the future. Just a suggestion.
Yeah, thank you for the suggestion.
Thank you so much, Mr.
Good afternoon, everyone. My name is Yukai Wang from KAIST Human Facts Lab, and my advisor is Nico Chen. Today, I want to share the topic proactive safety in autonomous vehicles, integrating world model and traffic conflicts. And this is my content. I want to talk about. First, I want to talk about the emerging challenges, like the background, and second, I will talk about the technicals for proactive safety, and then I will introduce my work, the ProSafe AV, and then I will conclusion. So first, as we all know, nowadays more and more autonomous vehicles brand are on the rise. For example, we have the robotaxi in Baidu, and Waymo, also Tesla recently published their robotaxi. And if we want to study the safety of the vehicle, we have two ways. The first, the reactive safety. If you want to use the reactive safety method, you probably need the historical cross data. And another method is using the proactive safety. It focuses on the predicting and preventing the conflict before they result in accidents. So because nowadays there are not too much cross data for the autonomous vehicles, so we need to concentrate on the proactive safety research. And here is some limitation of the existing methods of the autonomous vehicle. The first is the poor integration of prediction and decision making. Because most autonomous vehicle will use the reinforcement learning method to control the vehicle, and it lacks the robust conflict prediction. and also it limits the proactive handling of high-risk scenarios. Also, we need more data to analyze the autonomous vehicles scenario. So the normal IO system is highly really on the extensive real-world data, and it's high cost and impractical for real-time AV deployment. So next, I want to introduce the world model and the reinforcement learning. Do you hear the world model before? Probably most of you maybe not hear this word before because it's a recent, very emerging method in the computer science, and they use this combined with the reinforcement learning. And we can there is a definition of the world model. World models are generative models that learn to represent and simulate an environment. Instead of relying on the predefined labels, those models capture the dynamics of environment and predict future status. So you can imagine that how we see this world, and we can let the machine to learn let the machine to learn the world, how to change of this dynamic world. And so if we use the world model, so we can enable efficient imagination of scenarios and reduce the need for direct interaction with real-world data. Here I will give an interesting example to let you understand the world model. So if we can imagine that an AI learning to play table tennis, if we are the normal person, we didn't play table tennis before. We just want to catch the ball, and that's what the traditional reinforcement learning are doing. So the AI will learn to repeatedly hitting the ball through the trial and error. But if we use the world model-based learning, so we can imagine as a professional player. So when we catch the ball, we will consider the location where it will stay, and also the spin affect its path and how it pedal movement affect the game. So before actually hitting the ball, it can imagine the various scenarios internally, testing the different moves and strategy in its mind first. When we play if you are professional table tennis player, when you catch the ball, you can before your opposite hits the ball, you can imagine the road it will take. So here are the key components of the world model-based IO. It's very similar to the reinforcement learning. It has the state space, is to perceive the information from the environment, and also it has the action space. So it's the people to decide what to do next, and it also has the reward function. It helps to evaluate the policy. And also, just like human play the games, when we preserve the information, we need to decide what we need to do next, and also we need to evaluate our action. So why world model suits the autonomous vehicle? First, it has a better prediction and planning. So we can simulate the traffic dynamics, road conditions, and pedestrian behaviors. Also predict the potential hazard, and plan several rules, make proactive decisions. Also, we can enhance the sample efficiency. We don't need to more data from the real world. We can to generate more data through learning it using the world model. And next, I want to introduce the traffic conflict. And there is a difference between crash and conflict. As we all know that if there is a crash, there may be the injury or the death, so it will get the report from the transportation department. But if we have the conflicts every day, when there is a definition of the traffic conflicts, there is an observable situation in which two or more road users approach each other in space and time to such an extent, and there is a risk of collision. So there is no collision, just a risk of collision. And then there are four measures to numberize the traffic conflicts. First is the time collision. It's very famous one, and we only need know the distance and the speed between the two vehicles. And the second is a modified time to collision. It is acceleration compared to the time to collision. And the third is deceleration rate to avoid collision. So it not consider the acceleration. The DRAC consider the deceleration. And the last is post-encroachment time. And this is very useful for like not the two vehicles are not heading to the same direction. They are like heading to different direction, but like to vertical or another objective is a pedestrian, and there is a risk between vehicle and pedestrian. So in this situation, we will use the PET. And the next is the extreme value theory. This is the method I use to get the cross risk from the indicators I calculated. And there are two distributions I used in this extreme value theory. The first is GUA, generalized extreme value distribution. And the second is generalized Pareto distribution. If you want to use GUA, when you do the sampling, you need to use the block maxima. You need to pick the maximum or minimum through in each block. And if you want to use the GP distribution, you need to use the pick over threshold method. You need to decide a threshold. If the indicator, the value of indicator pass this threshold, it will be treated as an extreme value. So next I will talk about my study, like integrating the world model based IL with UVT to predict and avoid extreme conflicts. This work I present on the 2025 TRB, and it's still working because I want to add more experiments. And so this work, the objective of this study is to enhance the AV safety by integrating EVT for the conflict prediction with the world model-based IO for decision making. And the proactive approach can predict and prevent traffic conflicts, aiming to improve the AV reliability and safety in dynamic driving environments. And this is the whole framework in my study. It had the 4 parts. And at first, we need to perceive the information from the environment. So I use the sensor fusion, and then after we get the data from the environment, I have the 2 ways. One part of the data will go to the world model, and another data after calculation, I get the indicator and will go to the EVT part. And for the world model, it will connect with the IR part. So IR, you can think it as an actor. So we do the actions through this IR part, and also the evaluate through this IR. So in this study, I used the color simulation, and it's an open source urban driving simulator. It created for the autonomous vehicle research and development, and also is totally free. So this is my setup for the reinforcement learning. For the state space, I set as the representing the various observations using the different sensors. And for the action base, there are 2 kinds of action setting. The first is discrete. So we just set the predefined sets of acceleration and stereo values. So it can be negative or positive. So another is to set as continuous, but it's very use lots of computation cost. So I use the discrete way. Also for the reward function, there are many components, including the waypoint reward, speed reward, collision penalty, line keeping reward. Also I added my own UVT-based risk reward here. And the sensor fusion in Perceive is very based on this color simulation. All the sensors like camera, LiDAR, bird's eye view are using the color original sensor setting. And but I need to use the sensor fusion to combine all the data, and also to calculate the safety indicators, here I use the TDC and DREC. For the experiment, first of all, as I told, I use the CarDreamer is one of the open source world model algorithms, and based on the color platform. And for the hardware, I use NVIDIA RTX 4090. And for the sensor fusions, I use 3 sensors: the camera, bird's eye view. I treat it as a map information and the LiDAR information. And here is the training result. There are on the left there are 4 like metrics to represent the training results. One, the first is the reward rate, a reward score, action means, and here the score is generated by the color itself. And so, and also you can see those 2 GRFs. It shows one of the scenario during training. So you can see it's the car, the ego vehicle just accidentally stop at the middle of the road. So it's like he need to upgrade. And here is this is the final result. This is one of the world model results. So on the first line there are many moments I caught from the simulation. And the second line is the imagination. This is generated by the world model, and we can see the difference in the third line. So we can see most of the moments are are the same. So only the last one there, the world model generate a wrong car in the middle. And here is the EVT results, and there are 3 parameters in the EVT distribution, and also on the left corner there, this is the calculated cross frequency. So you can see that it will descend at last. And at the last, I compare 3 different methods: the DreamV2 and DreamV3, also my proposed method post FAV, and you can see that my method can work successfully on the mission. Here I give the mission is overtaking the front car. And this is a comparison result. The first is the average TDC. You can see that the post FAV has the bigger TDC, average TDC. That means it will be safer. And also this, the second is the score, and the last one is the average speed. So we can see that also my proposed method have safer behavior, but its average speed is not that high. So to conclude the comparison results, we can see from this table the ProSafe AV outperforms DreamV2 and DreamV3, achieving the longest travel distance and highest time to collision and perfect safety with 0% collisions. It also scores the highest overall, so demonstrates the superior balance between safety and efficiency. So for the conclusion, so the ProSafe AV that I proposed method enhance the autonomous vehicle safety by integrating the proactive safety with IO techniques, and also the balance the safety and efficiency in complex driving scenarios. Also, there are many interesting directions in the future. For example, we can expand the scenario diversity. We can to realize some cross scenarios in the simulation, and also we can bridge the simulation and reality and use it in a real vehicle. There are some research using the world model to generate some scenario using the real world videos, but it's not used on the autonomous vehicle yet. So that's all my research. Thank you very much.
Thank you very much, Mr. Luca. The floor is now open for questions.
Thank you for your great presentation. It's really interesting to me. Could you show me the slides about compare the three methods?
Okay. You mean this table or the figure? This?
Both, yes.
Yeah.
In the images in there, I see the screens are shaking left and right. Can you explain why the screen is shaking like that?
You mean the red car is tracking the green car?
Yes.
Yeah, that's in this scenario, my mission is to overtaking the green car. So the red car need to overtake it and reach the destination. You can see the Persephone can finish the mission very well. And here is my destination at last. But for the Dreamway 2 and Wave 3, they have some failures. So that's why I think my proposed method can outperform them.
Thank you for answering.
Okay, thank you.
Other questions?
And I think the last question, why the screen is shaking, maybe it follows the direction of the right community.
You mean the shaking, right? Yeah, that's also a very necessary research question now. Because if we use IO method to control the vehicle, most of the car will shaking, and so they have some new method to stop shaking. And if you find the way to let the vehicle cannot stop shake like this, you can publish a new paper.
The first one is we use 4 indicators to measure the traffic conflict. So what's the difference function of the indicators?
The first indicator is time collision. What I said is many research also the other researcher will use this indicator. It's just consider the car in front of you, and you can see from this function. It's the first here is the distance, and here is the speed. So it can get time value. The time value is based on the related distance and the related speed. So this is this is the name time to collision. And for the modified time collision, it not only considers the speed and the distance, it also is the acceleration. You can say the delta A. So we can see if you keep this acceleration, what time will you have a collision on the front car. So it consider not the speed, the acceleration here. So for the third indicator here, it not use if you not the acceleration to the front car, you use the acceleration. So also it also calculates the deceleration rate to avoid collision. So it's not the time here. It's the acceleration. It's also the unit is the deceleration. Also the last one is a post encroachment time. So it's also it calculates the time, but it's calculates the. For example, here is an area okay, I will show you this area. The red car just passed this area, right? So another car will pass this area in the future. So there is a time difference. So the PET is calculated. You can consider between the vehicle or the pedestrian and the vehicle. You just decided on the area you set. If you set this area on the crosswalk, you can calculate the PET between pedestrian and the vehicle. Yeah, PET is just calculate the time. And the object just pass it, and another object will pass this area.
Okay, and you also use the V1, V2, and the V3 as the comparator.
Yes.
The two methods, a baseline method or short-term method?
There are two baseline methods. Those DreamWorld V2 and DreamWorld V3 are like also very classical word model based reinforcement learning. So so at present I'm trying to do more experiments using other like IL methods like DQN, PPO like this. So here I just use a classical word model based IL method. Yeah. Thank you very much.
Thank you. I think there are more questions.
Okay, welcome.
Sorry, can you check if your microphone is working?
Oh, okay. Hello.
I don't think it's working. Can you check?
Hello. Do they have the electric? Maybe it died. Okay, I just speak loudly. Okay, you can see.
Thank you so much for this presentation. Very nice idea for this conversation. So you mentioned about extreme variable theory. So I didn't see the application of this methodology during you create a word model, right?
Word model.
When you create a word model, did you implement this kind of theory inside it? Or you just a way to visualize the result of the word model?
You mean where do I use the word model?
Like how the extreme various models
Ah.
your word model creation.
I can tell you through this framework. This part is for the EVT model. It not connect with the word model. It only predict the predict result. For the EVT model, the predict result is the crush frequency, and for the word model, the predict result is like the future status, and so we can all these predict result can put input into the critic. In critic, we can like evaluate our action in the reinforcement learning. So it can help us like do the better action in the future. And so also here one model, you can see in the middle, there also a line input into the IO. That's the like latent status. Latent status just we get the like low dimensional data from the perception, from like all the sensors fusion. We cannot input the like high dimensional data because we have the computational cost. So we need to like we use the encoder to decrease the dimension of the data. Like input this into the IL to let IL know what happened now. And also there's the decoder to generate the future status to let the IL know what will be in the future, like future status. Because IL can only perceive the environment using the status. Yes, so there is no like relationship between the word model and the EVT model, but they can all of them can like represent some information from like our present like word using the status. Yes.
The second question is about the result.
Okay.
You showed the result of the V2, V3, and post-AV.
Yes.
So about the average TPC. So I have two questions on that. So first question is when we say TPC, like generally people define like, okay, let's say when TPC is smaller than 3 seconds, then it's a crash. But when TPC is higher, right, it seems like let's say in real life.
Yes.
7 seconds, 8 seconds, 9 seconds, let's say 12.65 seconds and 7.94 seconds, they are exactly the same actually.
Yeah, that's right.
So how you gonna like evaluate these? Like the larger the better, or like
because
how you compare these
you're right, because we in real life like if the TTC is bigger than like 5 seconds, it's just like the normal driving, right? So maybe here, when we input the TDC here, it's just calculated by our program. So it's just like a data shoe, like present here. So maybe in the future I will consider like if the TDC is bigger than 5, just let it go. Yeah, I will.
And
Okay.
I'm also wondering, as also, when other professors were concerned, like you create a work model to make the TDC very huge, which means like it becomes more conservative. Like it will behave very, very safe.
Yes.
So which means a car passing out stop, so it's a high TDC. And you also consider that into the critics. So I'm wondering, will this kind of consideration of the safety influence the original behavior of the vehicle movement? For example, like all the vehicle will behave very slowly for the just like I'm not going to accelerate. I will be very, very safe. I will.
Yes.
I will not behave like the real world.
Yeah, that's the problem. We can see like there also I calculate the speed. You can see the speed is very low. So that's also what I concern. Maybe in the future I need to increase the TDC just like what you said. Maybe I said that if the TDC is bigger than 5 seconds, just let it go. And I only consider the TDC is less than 3 or 5. So maybe it can increase the average speed. So you can see from this row, the average speed is very low. That's also I need to improve in the future. Yeah, thank you.
Thank you for your answer. Thank you for the question. I think we still have room for one final question before we proceed to the next presenter.
Thank you.
Thank you.
First off, your research is very fun. So the red part, all of that red part shapes, the collision and adult lane, that's still 0%, right?
You mean here, right? Yeah.
So that shakes, but still no collision. But
The shake. Yes, it shakes.
Okay.
It's not perfect.
Yeah, can you, it was also interesting to, you showed us a distribution, right? In the back side before, I think?
Here?
No, wait before. Yeah, that part, you showed the action.
This is for the action distribution, yes.
How should we interpret that distribution?
Okay. For the x-axis, it's like the episode. Like from maybe here I have more than 25,000 episodes, and maybe the y is episodes. And as I told before in here, for the action space, I use a discrete action space. So here are the one is for the acceleration, and another is the steer values. Acceleration is to control your accelerate of this deaccelerate because they have the negative value and to the positive value, and also the steering value is control your whether you are turn. Like you have if you turn left, maybe you can be the negative 0.1. If you want to turn right, it will be positive. So here you can see maybe it's too small. There are many like discrete values. That means here I just consider two because one is for the accelerator, another is for the steering. And if it at last it will be always do the same action at last because the model think is the final optimized action. It will always do the same action at last. Can you understand? Because if it do the same action, it can get the biggest reward. So through this distribution, at last there is no more random action. Just do one action at last. Okay, thank you.
I think you can have more time later to discuss that. I also have some questions to
okay.
discuss that later. Let us move over. Let's give a round of applause to Mr. Yu Kai-Long.
Thank you.
Owen Xuan from TOPS Lab. And thank you so much. I can share with you my research. So in my research, I focus on how do drivers evaluate the environment. While we all know the objective crash data have been widely used to inform transportation policy, but the driver's subjective perception can also shape or influence their behavior. Like, they will driving more aggressively when they're feeling too safe. And let's start with the introduction part. So first, let's look into some background information. According to the World Health Organization Global Status Report on Road Safety, road injury accounted for 29% of global injury deaths in 2019, which making it a major cause of premature deaths. So which means the majority of road injury deaths are from under 60 years old. So, and when we look into the reason of road traffic injury, they also have studies show that 90% of the road crashes are attributed to drivers-related factors such as decision error and performance error. In that case, we want to understand how drivers' behavior can influence the road safety. This is also the start point of this study. So having seen the overall background, let's now focus on the key concept of this research, driver subjective safety perception, which describe a driver's internal judgment or feeling of safety within a traffic environment shaped by visual cues, past experience, and situational awareness rather than quantifiable risk. So if we understand more the driver's perceived safety, it can help us to build safety assessment and also the human-centered design. And this is our flow of the driver's perceived safety. What are the drivers saying on the road? And who are the drivers? What are their characteristics, their age, gender, or accident experience or driving experience. And based on this, how they evaluate the environment, assess the risk, and make the actions. So here we find that when drivers underestimate the risk, they may drive faster to compensate. And if they overestimate the risk, they feel unsafe on the road. So they are more likely to do conservative driving. So we can see that actually in the road environment will not change, but different drivers have different actions based on their perceived safety. So our object of this study is to understand how drivers evaluate the street environment and perceived safety. Next is the literature review part. So the first, I'd like to introduce the research on perceived safety. Actually, this research has a long history and not limited to the transportation domain. In the very early age, researchers focus on the conceptual foundations. So they identify the factors that will influence the risk perceptions. However, there are lack of perception quantification tools. And then is the second stage. So in the second stage, with the release of Google Street View in 2007, the Place Pulse project emerged, using the large set of Street View images for crowdsourced perception experiment to collect urban perception data. However, in this stage, researchers, they also introduced the Q-score to quantify the perception. But they only considered low-level visual features. And nowadays, there's more and more researchers pay attention to this area. And because we have more advanced deep learning techniques, so we can extract the image visual features more exactly. And also, we can do some prediction here. However, they have two research gaps here. So the first one is the limited interpretability caused by the black box model, and the second one is the efficient exploration of meaningful interaction effects. Then let's narrow down to the traffic safety perception. So the study in this area, actually they have some relationship. Some researchers, they find the built environment and the actual risk, the relationship between built environment and actual risk. Some study, they focus on the built environment and perceived safety. Some focus on the social demographic features and perceived safety. Also, they have some researchers want to figure out, is there any correlations between the actual risk and the perceived safety? It's very meaningful, but have some challenge because we need to solve two problems here. The first one is how we get the perceived safety, and the second one is how we can relate the objective risk and the perceived safety. And in my research, I will focus on the first questions, how we get the perceived safety. So the first challenge here is how to collect driver subjective perception data. So from the past research, we identified four popular methods for collecting perception data: rating scales, stated preference, interviews, and pairwise comparison. And here we will use the pairwise comparison. We have several reasons. So the first is we have previous study, such as PlacePal's project. They use street view image to gather urban perception data. And also their dataset has been widely reused in both urban and traffic research. And second, the pairwise comparison method have also applied in other fields, especially using in the image evaluation. So some medical researchers found that compared to the Likert scale, pairwise comparison can improve the reliability of evaluation in CT image experiment. And other scholars have shown that the fourth choice pairwise comparison produced the lowest variance and the most accurate result. So therefore, in this study, I applied the pairwise comparison to collect drivers' perception data. So the second things we need to consider is the perception model choice. So they always have debating between statistic model and machine learning model in perception study. The reason is people want to figure out how they perceive the environment, and they want to do some prediction here. So they have the different direction. Based on the different direction, they will choose different model. However, back to our goal of this model, we want to quantify how environmental features shape perception. We want to compare groups like age, gender, or driving experience. We want to look into how interaction will influence perceptions. So here, we'd like to introduce a glass box between the white box and the black box. And now, let me show you the methodology sections. The first is the image dataset. We are using the Mapillary Vistas dataset, which contains 25,000 images covering 6 continents. So compared to the Google Street Views, this dataset offers more distinctiveness in building types and road structures. They're providing a greater diversity for perception study, which is easier for our respondents to respond to questions. So in our research, we select around 6,000 images and use them in the survey. And in the right side is the example and the detail of this dataset. So the next is our survey design. As you can see, in our survey, we have 2 parts. The first is social demographic, and the second is pairwise comparison. So in the pairwise comparison, each participant is showed 150 image pairs randomly selected. And this is our survey. The right side of this slide you can see our result. So in total, we collect 500 questionnaires and 75,000 pairwise comparison record. And below them is the demographic distribution of the respondents. Our research framework is designed to simulate how drivers behave in real-world driving experiment. So in the task 1, we collect street view image to describe the road situation. In task 2, the survey gathered both social demographic data and pairwise comparison data. In the task 3 and task 4, we are focusing on modeling. We structure the combined data and feed it into the model, which then provides interpretable analysis, include global importance and the main effect plots, and also the interaction heat map. The first is task 1. Although they have a lot of computer vision techniques, here we are choosing the objective detection and image segmentation here. So the workflow and example and the data sample are shown below. So in the task 2, we process the survey data. So as you can see, each image, they appears in around 25 years to ensure the stable ranking. And then we want to get the global rankings, so we apply the ranking algorithm here. That means we also have the chosen tool is called score difference. So while both of this output compared image A and image B, but they capture the different signals. So chosen reflect the participants' raw individual judgment, while score different reflect system level aggregated perception signals. Next, we notice that the data are from 2 different levels. So the survey data from the respondent level, the image data from the image level. To combine these 2 data sets, we first transform the survey data from wide format to long format. And then, to contract the perception deviation feature, we calculate the difference between the image A and the image B. This final step allows us to prepare the structured input data for modeling. So our task 4 is our model. This study applied the explainable boosting machine framework. So this is known as the glass box model because it has a clear mathematical structure that is human readable, explainable, and fully visualizable. Also, you can see from the image is the training process. So in the stage 1, we are modeling the main effect. So the model using the gradient boosting on shallow trees to learn each variable's effect. And in the stage 2, they are modeling the interaction effect. So they detect the key pairs and features using the FAST algorithm. So here you can see from the output, actually you can see every single sample, their contribution in the model. So we can output the main effect plot and also the interaction heat map here. So after the methodology, I'd like to introduce the result and discussion part. The first result I want to share is the model performance. So here, as you can see from the table, we test 2 types of output variables, the chosen and score difference. So in summary, the model performance clearly varies depending on the output type. With the chosen output, the random forest with top 20 features performance the best, and the EBM as follows. But with the score difference as output, the EBM achieved the highest accuracy and AUC. So this result also matches the finding from related place pulse studies as shown in the table on the bottom right. So why we have difference between the different output? Actually, it's because of the ranking models. The ranking models treat all raters as interchangeable and ignore who is making the judgment. So as a result, score different, actually they flatten the individual and group level effect. Also, when we back to a previous study, they find actually they have some difference between the different demographic groups. So in the rest of the result and discussion part, I'd like to show you the result from the chosen output. Our first finding is from the main effect. So here you can see some of the main effect plot. These show the trend between each single variables and perceived safety. So on the plot, the X presents the difference features value between two images, and Y shows the contribution score in the model. In summary, we observed that more vehicle, building, people, and riders tend to decrease perceived safety. In contrast, features like sky, fence, or poles tend to increase the perceived safety. Additionally, some traffic facilities and non-motorized vehicles such as motorcycle, bicycle, and traffic light, they showed fluctuate or nonlinear effect on the perceived safety. And then I'd like to highlight a few interesting plots, more detailed. So when we look closer to the detail, we see some interesting patterns. When the number of buildings increases, the driver, they feel less safe. As we mentioned earlier, when people feel less safe, when people feel unsafe, they tend to adopt more conservative driving. On the other hand, when the amount of sky increases, the driver will feel safer, showing the opposite effect. Also, when we look into the traffic light, we can see if the traffic light is much more or clear and visible, like image A, then people will feel safer in that scenario. And if the traffic light is just slightly more or unclear, then which showed in image B, that means their perceived safety actually decrease. This suggests that actually drivers, they tend to driving on a place with well-structured environment. Next, I'd like to introduce the introduction effect. So after analyzing the model, we found that different type of feature combination contribute differently of perceived safety. Especially the road static infrastructure and traffic participant is the most common interaction in category level 1. And in category level 2, the key interaction are motor vehicles with pedestrian and riders and motor vehicle with safety features. This pattern highlights that it's not just individual variables, but the way they combined that shape safety perception. And this combination reveal new insight beyond what main effect alone can explain. So the second is the combination of two factors can change perceived safety direction. Before I explain, I'd like to introduce the heat map for you. So as you can see, the red area means people prefer that environment, and the blue area means people feel unsafe in that kind of area. So when two different factors combined, you can see clearly which kind of area will make people feel unsafe. So here, we can see in the main effect, the car and the person will both decrease people's perceived safety, but when they combine together, if their number are much higher than the other image, which means they feel safe on that kind of environment. Also, the more safety infrastructure does not always lead a safer perception if they combine with other factors like the fence and the bicycle. So if image A's bicycle number is over image B and the fence is fewer, that means that environment is make people feel safer. And if drivers driving on an environment with a lot of bicycle but a lot of fence, which means they will feel unsafe in that kind of areas. And the last one is the interaction between the social features and image features. So here is the overview of the result. So we can see the older drivers tend to prefer fewer cars, fewer signs, and more open spaces. The female tend to prefer signals and vehicles. Males prefer simple environment. And less experienced drivers prefer more cars and enclosure. Experienced drivers show the opposite. People with more accident history prefer more cars and human. Mixed commuters, they prefer more cars. Long-distance travelers prefer fewer. Cautious drivers tolerate more people, and confident drivers prefer less people. And here is the example. As you can see, the red area, which means the older people, they prefer less vehicle. However, the younger people, they prefer more vehicles. And now, let's wrap up with the conclusion. So to conclude, let me briefly summarize the main point of this study. So we analyzed the perceived safety based on interpretable feature contributions. We evaluate both individual effect and interaction effect using EBM model. And we identified patterns across street view features and social demographic groups. The main finding and contributions in this study is we built an interpretable modeling framework to combine the image features, the respondent's perception, and the demographic data. We also identified nonlinear and interaction-based determinant of perceived safety. We mapped how social demographic shape preference patterns. But we also have some limitation here. So the first is interpretation are perception-based and not directly tied to the real crash data. And the second is interaction analysis is limited to pairwise effect due to the model constraints. So our model actually they can only detect two-dimension interaction, but they cannot detect the higher dimensions. So in the future, we want to incorporate the contextual variables like traffic flow, lightning, and time of day to enhance the perception modeling. And we want to integrate the actual crash data to examine the gap between the perceived and objective safety. We also need to extend the interaction analysis to include higher order effect and more complex relationship models. And this is the reference. Thank you for your listening.
Thank you so much, Ms. Ho and Sean. The floor is now open for questions from the audience. I think we have room for 2 to 3 questions. If we're following the schedule, we have 5 minutes for Q&A. Yes.
Thank you for your presentation. I have 2 questions. The first question is, why did you focus on the influence of social characteristics on perceived safety?
Why I didn't?
Why did you focus on the influence of social characteristics on
Yeah, actually I think that is from the previous study, because I find actually the previous study, they are separate. Some people, they are consider the social demographic and the perceived safety, and some people, they consider the visual factors with the perceived safety. So I think if I can combine them together, it will be better.
The second question is, given the discussion on the relationship between perceived and actual risk, how do you plan to integrate the two types of data in your future research?
Yeah, I think that's one of the reasons I apply the ranking algorithm here is I want to find the better ranking algorithm if they can increase my accuracy. Then, which means I can build a model to have the results from other place perception data. If I have that perception data, then I can relate it with the actual risk data. Thank you so much.
Thank you so much. I think we have room for one more question for us. Oh, sure.
Thank you for your presentation. Your topic is really interesting, so I really enjoy your presentation. I have two questions, and the first one is, did you find some difference between like highway and urban road, like similar detections?
Yeah, I think that's a good point, but in this study, no, because I think my data set, they didn't have the label of the highway and the rural area and the urban area. But if we have the further data set we can use, then we can add the label into that model, then we can find something there.
Okay, and my next question is, do you think about your research to adapt to like automated vehicles, so we can use to control the speed of the autonomous vehicle?
Yeah. I think maybe it's too early to say here, but one of the reasons I do this study is I want to to influence or control the driver's actions. Also, it can also be the order to the autonomous vehicles. So if we can adjust autonomous vehicle in the road depending on the different environment, I think that will be a good there will be a good attempt here.
Thank you.
Thank you. I think that's it. I think part of your research that really interests me, especially with policymaking and infrastructure modification, is the part when you said about their feelings about more safe and less safe. And then if they feel more safe, the possibility is they might lead to risky driving. So it also leads to any questions if do we make policies to make them feel something so that they will turn into more safer driving practices. But that was a really good presentation. Thank you, Ms. Owen.
Thank you.